Okay. So our next talk is about serving, large language model serving, and it will be presented by Han-Chen Lee. Han-Chen is a rising fourth-year undergraduate student from University of Chicago, advised by Jun-Chen Jiang. His current research interest is in systems and networking support for multimedia and AI workloads. He's looking for PhD position in the next year, so faculty, please look and talk to him. Okay, so his talk title is CacheGen, KV cache compression and streaming for fast large language model serving. Yeah.
Thank you for the introduction. So today I'll give this talk on CacheGen, KV cache compression and streaming for fast language model serving. This work was done by the University of Chicago, Microsoft, and Stanford University. Just a quick introduction on the first author, Yuhan Liu. She's a rising fourth-year PhD at Chicago, advised by Jun-Chen and Shan. And she's amazing, so look out for her in the following years. Nowadays, large language model inference are equipped with context. For example, in this ChatGPT session, the user first gives a document that is Amazon Company 2023 annual report, and then it asks this question: what generates most operating income for Amazon in 2023? So, although the model was probably never trained on this specific document, it is able to give a very accurate answer due to the presence of this context. Since these kind of documents, they provide necessary background informations, we will call them context from now on. And similar applications including retrieval augmented generation, or you may call it RAG nowadays, and also like agents with conversation histories are becoming more and more popular these days. So the problem with using these contexts is that processing long context can be very, very slow. So this is the same example that you see, except we are now feeding into a Llama 70B model. It's running on 4 A40 GPUs. So what the model will first do is we'll go through a phase called preview. This preview processes this long context into an intermediate form that a large language model can understand and use later. And after this preview of the context, what you do is you preview the user query as well. It's taking a short amount of time, but only after this time you can get an answer. And notice at least 9.5 seconds before the user gets any response in this case. So why do we do this lengthy preview? The reason why we do it is because it produces an intermediate form, and this form is called KV cache. So think about the KV cache as two 3D tensors in PyTorch of shape, number of neural network layers, number of tokens. Tokens here basically means it's a unit of language processing, like it's slightly less than a word. And then number of channels, it's just hidden states of neural network that is used to scale up the model, but it doesn't really matter here. So the good thing about these KV cache, like why do we take them out separately, is you can reuse them. So still the exact same scenario. You get the KV cache, you get the answer. And then the second question came. What generates the most profit for Amazon in 2023? It's a different question, but it probably uses the same annual report in this case. So what you could do is why don't you just reuse it, right? So if you reuse it, you don't have to do this lengthy preview of context. You can just preview the question and then you get the answer. But in real life, this is not the case. KV cache might need to be transferred through a network link, or through a like storage device to your GPU, and this causes a problem. Before we say what the problem is, let's first see like why like you need to transfer. The first reason is volatile memories cannot hold all KV caches. So still the same scenario, except you now store KV cache in GPU like server number 1. And then many other requests comes in before. The second question came, and then your KV cache just got evicted because there's simply no space for it. So when this second question came, it's not inside GPU. And you may think, okay, let's do it with CPU. But if you are running a very successful, let's say, AI startup, and then a lot of users want to use your service, and this might not be the case. So just a quick comparison about this. So this is A40 GPU, and if you store like Llama 70B 16K token context in there, you can only put 9 of them. And this is like a graph showing like if you increase the context length, the size of it also increases. And nowadays, a lot of AI people, they want to create long context models because that gives them more capabilities of interpreting complex sources. So another use case is you might want to reuse KV cache across different servers. So this is the first request is directed to server number 1. The second question came, and you have many servers across the world. And then this question just got directed to server number 2 because server number 1 may be busy doing something else. And then you might need to load KV cache from the server number 1. And they might not be in the same region, or like they might not be connected with, say, like NVLink. So the goal of CacheGen is this. You have this very naive pipeline that takes 9.5 seconds. And if you take the original KV cache and you send it through a not that fast network link of, like, say, 3 gigabit per second over the wild network, it's going to take 14 seconds. However, if you compress this, that's what CacheGen wants to do. If you compress this and then you send it through the network, it's going to be much faster, and you spend a small cost decompressing it such that the overall delay is slower. So here's the demo. The demo is showing basically on the right, you see the CacheGen paper. The archive version, like, it's pretty old, but it doesn't matter. On the left is the control panel. We're going to ask this question: what are the data sets used in this paper? Answering 5 words. Let's see how it goes. So now it's running. Now it's running the preview. Okay, so you see, like, the answer is generated after 7.16 seconds. It might be fast enough for a human user, but for a machine, you can do better. So this is what CacheGen does. On the top left, you can see we got this caching enabled, and it's the same scenario, same question. Now I'm going to run it. 3, 2, 1. I'm going to push. Okay. And then this actually gets a much faster response. There is still optimization to be done in this repo, but like it's like a lot faster than the original version. So here's how we do it. This is the end-to-end system overview. We take the original KV cache, which are 2 3D tensors. We compress them into bit streams, and then we put them in a storage device offline. And when needed online, it got loaded into the GPU, and then we perform a GPU-based decompression, which is super fast. And then you get this decompressed KV cache inside the GPU memory you can readily use. And so, like, the key component is the compression, and I'm going to be mainly focusing on this in the technical part. So the key insight behind CacheGen is that instead of the prior works, mainly in the machine learning community, you compress them into the same tensor format. You compress them into bit streams. So here's something to say about this here, is that these machine learning works, they mainly compress into tensor format because they want to enable more batching inside a single GPU, and they're going to call this KV cache pretty frequently. So you don't want to transform every time you use it. But for CacheGen, since you're already transmitting it over a network link, like, why don't you just compress into the most nature form, like, which is the bit stream here? So that's the rationale behind, like, why you want to compress this into bit stream, and then you will see later on there are a lot of optimizations enabled by compressing to bit stream. It's worth noting that you can also apply CacheGen on top of these machine learning methods, and it actually works very well. I'm going to show it to you guys later. So stay tuned. Don't leave now. So here's number 1 opportunity brought by compressing into bit streams. So this is KV cache of nearby tokens and similar. So what does it mean? So this is a heat map of single layer KV cache in a model. The y-axis is the channel, which is the hidden layers, and the axis is the tokens. It's kind of like you can do something today, and then, like, these are tokens. So this might not be too clear. By the way, okay, so the lighter the colors are, the larger the values are. So we zoom in a little bit, and here's what you see. The values are similar if you take nearby tokens and you just compare them, they are similar. But, like, if you take values farther away, they are more different. So what we do in CacheGen is we compress the delta instead of the original values. So how do we do this? So this is the key cache at layer J. You first separate them into groups. So a group is around, like, 20 tokens. You set the first token in this group, we call it an anchor token. You save the original value for the anchor token. For the later values, instead of saving the original values, you save the difference of this value from the anchor token. And you do the same thing for different groups. So here's what you get. So this is the heat map for KV cache after you do this delta. And as you can see here, like, almost all points are 0 now. And this greatly decreases entropy, which is going to be beneficial for compression in arithmetic coding. And here's what arithmetic coding does. It takes input distribution of the symbols you want to compress. It takes the symbol, of course. and then it gets you a bit stream. So for those of you who are not that familiar with it, the very important property you need to remember today is that the more skewed the input distribution is, the smaller the size will be after the compression. So what it means is that the rationale is if you have lower entropy data, so let's say you have 90% of symbol A and 10% of symbol B, it's much easier to compress than you have like 50% of A and 50% of B because it's like more random. So you want to have this skewed distribution. And notice that the previous like delta compression already gives you like a lot of zeros, but we still want to decrease more entropy. So this graph is a little bit complex, but I'm going to break it down in a bit. So the y-axis you can think of as like entropy or like some bit per element. And these bars are different methods. The blue bar is the most naive method. You don't do anything to the key cache. You basically take the key cache as a whole, and then you do arithmetic coding on it. And for grouping by token means that for each token ID I, you take all these KV cache with token index equal to I, and then you do arithmetic coding to this group, and then you do the same thing for each two groups, and then you add them together. So what CacheGen does is this. We basically, as you can see in the graph, you can see that grouping by channel and layer is better, so we just do them both. But if you can do all three of them, because otherwise it's going to fall back to the blue line. So we just group by channel and layer and save the small size. And the last insight we have is kind of like a quantization finding as well. So it's that later layers endure more loss. So this is the accuracy under the same running loss. If you apply loss to earlier layers, the error is going to propagate to later layers during the computation as well. So you could do more quantization, more aggressive quantization for later layers. So this is a compression workflow. You take the original key cache and V cache, you do delta encoding, you do smart arithmetic coding, and then you do layer quantization, and you get this bit stream. So it was noting that we try to minimize the decompression overhead because it's slow to decompress with CPU. So what we did is we wrote a CUDA kernel, and here's a very simple comparison of like how preview and decompression varies in the amount of computation needed. You can see decompression is almost invisible right in this graph. So I'm just going to jump into evaluation. So the evaluation is done on like some AI data sets with a simulated network link of like 3 gigabit per second by default. And we're going to report size of KV cache and time to first token. You can think of it as total preview delay. So the key finding here is CacheGen have more efficiency with very high accuracy. So the x-axis in this graph is size of KV cache. Y-axis is the accuracy in the data set. So this is the quantization baseline of 8-bit quantization, 4-bit quantization, and 3-bit. And if you see how CacheGen performs, it actually saves 4.3 times the size without without significant amount of accuracy decline. The similar graph, but this time it's delay on the x-axis. This is quantization. This is a naive preview, and this is how CacheGen performs. It's a 3.7 delay saving under this scenario. And you may ask, what if we vary the bandwidth? So in this graph, the y-axis is TDFT, the delay, and the axis is the bandwidth that you use to send the KV cache through. Preview is not affected at all by the bandwidth because you don't need to send anything through. And then this is quantization baseline, and this is CacheGen. So CacheGen significantly performs all other methods in a wide range of bandwidth. It is worth noting that you may argue that if you have very high bandwidth interconnect, then you don't need CacheGen at all. Actually, it's not true because remember that CacheGen saves storage for you as well. It's almost a 4 times storage saving. So you could either put more KV cache in your storage system, or you just save money by using less SSDs or stuff. So here's the graph that I promised. H2O and LM-Lingua are just 2 machine learning papers that does token dropping, but they try to compress them into tensor format, and they are very, very useful in some sense. But you can apply CacheGen on top of these methods. And here's what you see. You can see we also have a very large saving if you apply it to them. So yes, compressing to bitstream is actually nice. Yes, and in conclusion, smartly loading KV cache can save preview delay. CacheGen compresses KV cache into bit streams for efficient network transfer through custom KV codec. it reduces the size of KV cache by 4.3 times, and the delay to load KV caches by 3.7 times. By the way, here's the open source project that we're trying to build at UChicago. So the idea of this is you give a text document to this repository, and what you do is we will try to put the KV cache from like the storage device directly into the GPU. It got like cache and some other works in there, but it's not like, we haven't released the first stable version yet, but I think stay tuned for more updates, and I welcome any questions.
Thank you. Questions?
Hello, thanks for your talk. I have a question that since you do compression to KV cache to a bit stream, do you lose the quality of the output from the application?
So, okay, if you go back to this graph, okay, so first of all, a disclaimer, CacheGen is a lossful compression. It has quantization in there. Yeah. So, the delta compression and the arithmetic coding is lossless. But the quantization is lossful. So, you could see here, like it's almost the same quality as the baseline because they actually use similar quantization levels in this.
So do you make a comparison, for example, with a larger deep learning, with a large deep learning model without CacheGen and a smaller deep learning model with CacheGen? Maybe their performance is the same. So do you compare their quality of outputs?
So I think you might have made a mistake. Are you saying that you're comparing a smaller model without CacheGen and a larger model with CacheGen? Is that what you're
Yes, yeah.
Okay, yeah. So I think we've done similar experiments, but it turns out that the larger model with CacheGen actually performs much better. I'm not sure if I think it might be in the appendix of the paper, and I encourage you to read it if you're interested.
Oh, okay. Thank you.
Yeah, thank you.
Yeah, hi. Thank you for a great talk. This is Junyi from Huawei. So I have a question. So as you save the KV cache into the storage, so I'm wondering whether first of all, the access to the storage, like usually more than 100 microseconds, could that be a bottleneck? And another thing is that before you load the KV cache, you need to do the search first. So could the search procedure be the bottleneck?
Could I answer your second question first?
Yeah, sure.
Because, so if you think about it, are you asking like it's a search for the text document, or are you asking the search for the...
For the correct key. Like you have a key, you need to search for the cache, right?
Oh, yeah. So you need to do this anyways, like for searching.
Yeah. But I'm wondering whether that could be the main bottleneck of the latency instead of the loading process.
I see. So like if you're doing, say, like retrieval augmented generation, like these context-based stuff, you need to search for these contexts anyways. So what you could do is potentially just have a pointer that points from the raw text document to the first bit of this bit stream, and then you could just load it. I think, but like if you're talking about, say, like agents with conversation history, there might be some overhead, but like we are just currently studying this.
Okay.
So could you just rephrase your first question?
The first question is about the SSD access.
Okay.
Like that latency could be more than 100 microseconds. So comparing to your saving, could that be more?
I see. So you're saying like if the delay is like 100 milliseconds or 100 seconds or 100 millisecond, right? 100
microseconds for the SSD access.
Oh yeah, but if you think about it, like a preview delay, as we showed, it could be like more than 9.5 seconds. So like on that scale, I think like the access the small delay to access the storage device is not comparable.
Okay,
yeah.
I see.
So you can think about it as like using a not that fast device, like because like people do caching in like fast storage device, but you can think of it as like using these SSD as a caching layer for the large language model because they are much slower things.
Okay, I see. Thank you.
I appreciate it.
Let's thank the speaker again.